Welcome to The Explainer. Today we are taking a seriously fascinating journey into the invisible mechanics of thermal radiation. We're going to uncover the unseen quantum rules that dictate exactly how heat moves across our entire universe. It's going to be a fun one. Think about this for a second. How does the sun's heat actually reach us through the freezing, completely empty vacuum of space? I mean, we all know about heat conduction, right? Like touching a hot stove, and convection, like hot air rising. But those require physical matter to move the heat. Thermal radiation is this incredible third mode of heat transfer, and it requires absolutely no physical medium to travel. It literally just crosses the void. Okay, let's dive into this roadmap. First, we'll look at the nature of thermal radiation, then the ideal blackbody emitter, followed by interacting with real matter, the color of heat, and finally the geometry of heat exchange. This is going to take us all the way from the quantum origins of a photon straight through to complex engineering geometry. All right, part one, the nature of thermal radiation, the quantum beginning. So to really grasp this, we've got to look at the speed of light. Thermal radiation is electromagnetic radiation emitted by a body simply because it has a temperature. And here's the mind-blowing part. It propagates at the exact speed of light, 3 × 10⁸ meters per second. It doesn't just flow like a continuous stream of water either. It moves in discrete, tiny little energy packets called quanta, which are entirely governed by Planck's constant. Just look at how massive this spectrum is. Thermal radiation spans from about 0.1 all the way to 100 micrometers. What's really wild, though, is just how limited human perception is. See that incredibly narrow little sliver between 0.35 and 0.75 micrometers? That is the entirety of visible light, every single color we can see. The rest of this massive spectrum is just completely invisible to our eyes. You know, to strip away some of the heavy jargon and complex math just for a second, I absolutely love this concept from our source material. It suggests we can just picture this invisible energy as a photon gas. So imagine discrete invisible particles carrying energy, mass, and momentum physically flowing through empty space from a hot object over to a cooler one. It makes the abstract feel so much more relatable, doesn't it? Moving on to part two, the ideal blackbody emitter, the perfect absorber. Okay, so to make sense of this chaotic photon gas, physicists and engineers needed to create a perfectly idealized theoretical baseline. They call this a blackbody. It's essentially an ideal material that absorbs absolutely all incident radiation that hits it and reflects literally zero. Now, here's a really fascinating detail. The visual blackness of a surface can totally trick us. To our human eyes, snow and ice look blindingly bright, right? But if you look at them through the lens of long-wavelength thermal radiation, snow and ice absorb it almost perfectly. Thermally speaking, snow behaves exactly like a blackbody. Who knew? Now, the total energy emitted by this perfect blackbody is governed by the Stefan Boltzmann Law. The equation is E sub B equals sigma times T to the 4th power. Let's think about what this actually means in the real world. The energy radiated doesn't just scale linearly with temperature. No, it scales aggressively with the absolute temperature raised to the 4th power. So even a tiny little bump in temperature means an absolute explosion in the amount of radiant energy. And that sigma in the equation, that is the Stefan Boltzmann constant. It's an incredibly tiny, super precise mathematical baseline. Think of it kind of like a universal speed limit governing the total energy emitted across all wavelengths by an ideal radiator. All right, part three, interacting with real matter, the collision. Now, what's really interesting about this is that the universe obviously isn't just made of theoretical blackbodies. What happens when this perfectly modeled radiation actually crashes into a physical real-world wall or a piece of glass? Well, the very moment an incoming photon strikes a boundary, its energy is immediately forced down one of 3 possible paths. Let's walk through them. First is reflectivity, which is just the fraction that bounces off. Second is absorptivity, the fraction absorbed straight into the body. And third is transmissivity, the fraction that passes right on through. Since energy is always conserved, these 3 fractions have to add up to exactly 1. But here is the kicker for most solid objects. They don't really let anything pass through. For them, transmissivity is basically 0. It's all about bouncing or absorbing. When that energy does bounce or reflect, it happens in 2 main ways. Specular reflection is exactly like a mirror. The angle the radiation comes in perfectly equals the angle it bounces out. Diffuse reflection, on the other hand, means the incoming beam is scattered uniformly in all directions. Now, real surfaces are incredibly complex, and they're never perfectly one or the other. A really rough surface is going to scatter energy diffusely, while a highly polished one acts much more like a mirror. Which brings us to part 4, the color of heat, shifting wavelengths. To analyze these messy, real surfaces, engineers use a sort of bridge concept called the gray body. We define this as a surface where its monochromatic emissivity is completely independent of the radiation's wavelength. Basically, it's a consistent baseline we can use for real-world objects. This ties right into Kirchhoff's identity, which proves this really elegant rule. If a body is a great emitter of heat, it is equally a great absorber. And this brilliantly illustrates exactly why we need that gray body bridge. Over on one side, you have these beautiful, smooth, ideal curves of theoretical black bodies at various temperatures. But look at the reality of a physical real-world surface, that jagged, chaotic up and down line. Assuming a surface acts as an ideal gray body just lets us smooth out that chaotic curve so we can actually, do the math. Now, if you noticed on those curves, the peak of the radiation actually shifts to the shorter wavelengths as things get hotter. This is called Wien's displacement law, and it perfectly explains something you've probably seen in your everyday life. Think about heating up a piece of metal. First, it turns a dark red, but as you pump more heat into it and the temperature spikes, the peak radiation shifts down the spectrum and the metal turns bright red, then yellow, and finally a blinding bright white. Let me share this incredible real-world application from the source material, ordinary window glass. So, the sun is incredibly hot, around 5,800 Kelvin, meaning its radiation is mostly short wavelength, below 2.5 micrometers. Window glass is perfectly designed to transmit those short wavelengths, letting that hot sun right in. But the items inside your room are much cooler, sitting at around 300 Kelvin. They emit long wavelength radiation. So to that low temperature heat that's trying to escape your room, the window glass acts like a totally opaque solid brick wall. The heat just gets trapped. Finally, we arrive at part 5, geometry of heat exchange, the spatial problem. Okay, so now that we understand the radiation itself, how do we actually calculate the way two distant bodies exchange this energy across space? Well, the answer is the radiation shape factor, which is also known as the view factor. It's the precise fraction of energy leaving one surface that successfully reaches another. You see, heat transfer in a vacuum isn't just about how hot the two objects are. It is heavily, heavily dependent on the specific physical angles, the orientations, and the physical distances between them. Let's move to this and see how it builds. Imagine Area 1 and Area 2. The radiation intensity that successfully travels between them is completely dictated by the projection of their area normals and the physical distance separating them. If Area 2 tilts just a tiny bit away, the amount of thermal energy it catches from Area 1 just absolutely plummets. But here's the best part. All of this complex spatial calculus boils down to an incredibly elegant rule called the reciprocity relation. Area 1 times its shape factor relative to Area 2 perfectly equals Area 2 times its shape factor relative to Area 1. It's this beautiful mathematical harmony showing how surface area perfectly balances with spatial geometry to determine the net energy transfer between literally any two objects. So what does this all mean for us? I want to leave you with this thought. If our entire universe is filled with this invisible, geometric flow of photon gas darting around at the speed of light, interacting based on angles, distances, and temperatures to the fourth power, how is your own body exchanging thermal radiation with the walls of the room you're in right now? Think about it. You are constantly radiating heat to your surroundings, and they are radiating right back to you in this unseen light-speed dance of energy that literally never stops. Thanks for joining me for this explainer, and keep questioning the invisible mechanics of the world around you.